Mindsetters, grade 11s, it is your time, term 3. We're back, guys. I hope you guys are excited. I am Looney, and joining me in studio is Dina. Dina, how are you?
I'm very well. It's good to be here, and I'm excited for today's lesson.
Cool. So what are we doing on today's show?
Today's show, the first thing I want to say is to all the grade 11s I taught during the holidays. Hello, Tandeka, I know you're watching. And then I'll be doing some measurement that you've covered in grade 10, but I'll just be taking it a little bit step forward with a couple more of objects included into one unit.
Oh, okay, cool. So it's measurement, guys.
Yes.
So Dina, I'll send you to your board.
Thank you.
So Mindsetters, don't forget to join us and to watch and to just, focus and concentrate. Thank you so much to Macmillan for making the show possible. To keep in touch with us, guys, you can go onto facebook.com/learnextra. On Twitter, our handle is @learnextra, to download the show notes, the videos, the schedules, to check out the products that we have for revision and everything else wonderful and learning more and learning extra and all of that. You can go onto learnextra.co.za/live. Remember, guys, I do post the notes on our Facebook page. So just remember to like our Facebook page. I'll post the notes and any other information that you will need for the whole show. So with all that said, and thanks to Macmillan, Dina, straight to you.
Right, everybody, thanks, Looney, and I'm really, really excited because measurement's one of those sections in maths that really makes sense. It's very practical, it's useful, and for those that are always asking, where will I use this? This is the right topic for you. You're going to be finding shapes whose areas you want, whose volumes you want to calculate, and so this is the mathematics for you. For those who are numerically minded as well and love to work with the numbers and number crunching, this is also the section for you. So let's get straight into it. What we're going to do is have a look at the formulae that we've used previously, either in grade 9 or grade 10, because we're really not adding anything new. The standard shapes have remained. We're not adding any new shapes. So if you remember, from grade 10, we worked with the right prism, we worked with a cylinder, a right cylinder, we worked with a cone, and we worked with a sphere. And we've got formulae for the surface area, we've got formulae for the volume, so it's dependent on what we're working with. And it's all about working with the faces. So let's go and have a look at some examples. We'll go through the theory first, just to make sure that you are with us. And then I'll work through a couple of examples which showcase possibly what you've done previously is worked with one shape. We're going to combine shapes to form other shapes into a unit, and we're going to work with the unit's volume or surface area. So I'm hoping that you're going to enjoy the lesson. So let's start with the revision. As I said, we're going to work through a few examples to calculate the volume and the surface area, as well as looking at some scale factors. We're not going to do a lot, but we'll touch a little bit on that. And here is the key concepts that you've learned previously. Let's just extend the page there. There we go. So if we work with, let's do some coloring in, a right prism. Okay. The definition of a right prism is that it will have a characteristic face, and all the other faces are perpendicular to that characteristic face. So, for example, the very famous right prism that we know would be a cylinder. Because what you have is you have two faces that are circles, and then the other face, which is a rectangle, like a toilet roll. If you cut it up, you'll make a rectangle shape, and that face is perpendicular to the two circles. So in a right prism, the reason it's called right prism is because you have congruent faces facing each other. So another shape that you may have seen in the shops before is the Toblerone box. The Toblerone has two triangle faces, and then all the other faces are perpendicular to those two triangular faces. Hence, that is also a right prism. You could have a hexagonal base, and if opposite that hexagonal you've got another hexagon that's exactly the same, so it's congruent to that, then if all the faces are at are perpendicular to those two, then we've got a right prism. So that is the features of a right prism. So a very popular one would be the cylinder. So let's just fill in here. We would have a cylinder as a very common right prism. The volume of that shape is then very easy to calculate, because if you've got two congruent faces, then if you imagine you had to shrink that and you had to build it up, then my volume is really made up of stacking those circles on top of each other until I have the full solid. So the formula for the right prism is always just the area of that, we call it characteristic base, because it's what defines the right prism. So we would get the area of that base, and we would just stack those faces. So we would multiply it by the height of that prism. So very easy, just area of the characteristic base multiplied by the height. Now, the surface area is always the surfaces that you see. What is the area of all the surfaces that you see? And if you think about the cylinder, it has two circles that we see, and then it has a cylindrical portion. When you open up that cylindrical portion, it forms a rectangle. So the surface area, I would just determine which faces there are and work with the areas of those faces in order to establish. And so don't really go through formulae. I'd rather want you to understand how the shapes are formed to better formulate those various surface areas. Hence, it says the surface area is the area of all the faces. Okay, then we've got the pyramid. And the pyramid is a solid that's got a polygon as a base, but then it's got triangles as the other faces. And whereas a prism, you would have two faces opposite each other, the pyramid meets, all the faces meet at an apex. It's got an apex. A prism doesn't have an apex, a pyramid has an apex. So the volume of a pyramid is now given as a third of the area of the base. So now this has got a formula, a third of the area of the base multiplied by the perpendicular height of the pyramid. Remember that because we've got an apex, we would have a perpendicular height of the pyramid, and we would also have a slant height of the pyramid, which would be from the apex to the ground on one of the sides. Okay, so that's very different. So that would be the volume. Again, the surface area, because you've got a base with all the various triangular faces, you would just go to all the triangular faces and work out the area. So that would be the surface area, would be the area of all the faces. Okay, then we've got the sphere. Now, it's very difficult to define a sphere except as a perfectly round object. So a spherical object would be perfectly round, and the volume of a sphere is this very interesting 4/3 pi r cubed, where r is the radius of the sphere. Okay, and the surface area is 4 pi r squared. And this formula you must know because they don't appear on the formula sheet as such. Okay, and then the cone. Okay, so now you're very familiar with a cone. Cones have circular bases and a curved lateral face meeting at an apex. So whereas a pyramid has got a square face or a polygon face, a cone has got a circular face. And then its other side meets at an apex. It's a cylindrical shape that meets at an apex. And so the volume here is the same as the pyramid. It's a third of the area of the base multiplied by the perpendicular height. So you take it from the apex to the ground, perpendicular to the ground, as opposed to the slant height. And then the surface area of all the faces, where the surface area is equal to pi r squared, that would be the area of the base, and the cylindrical portion, this curved lateral face, would be pi times r, where s is the slant height. So s is the slant height. Okay, now you know all that from grade 10. That's just as a means of revision, and we're going to come back to this if we forget some of the formulae. But for now, let's go and have a look at our first question. Okay, now, question 1, imagine that this is the shape, or that this is a model of a capsule, a tablet, a pill that you take. Not a tablet like your iPads and your Samsungs, but a real one that you drink. Okay, a capsule is made up of this portion here and that portion there, which is actually half a sphere. So these two portions here make a full sphere. If we had to color them in, that would be my sphere. And then this portion over here is what kind of a shape? Okay, so any solid that you have been given that's made up of more shapes, you need to try and isolate the key shapes that you know in order to determine its surface area and its volume. So if we have to think that this is a 3D model of a capsule or a pill that you take, that you drink, then this portion, the pink portion, if we have to chop off these two blue portions, would give us a cylinder. So if we were working with a volume, we would want the volume of the cylinder plus the volume of the sphere. So that's in terms of volumes, because volumes is all about the kind of shapes that we have. But what about the surface area? The surface area would be made up of the pink portion, if it's a cylinder, would constitute that rectangle, and then the surface area of the blue would be the surface area of a sphere, because if I had to put these two together, I would get a completely spherical object. Okay, so now the dimensions that we're given, can you see? We're given that that's 0.75, or just 3/4 of a centimeter, and that's 1.5 centimeters from either side. Now, if that is a sphere, then that would be the diameter of the sphere, which would give you a radius. So if we had to write it down, then the diameter is 0.75. Then the radius would just be half of that diameter. Okay, and that would give me the radius of the sphere. It's sometimes good to just represent with a little acronym, a little subscript, just which shape you're referring to. It helps to denote that various shape. And then if we had that as my radius of the sphere, then my radius of the sphere goes all the way there. So from there all the way to that point would be half of 0.75, and the same thing would happen here to the end there. So this cylindrical portion, just this portion of the cylinder here, would have to be 1.5 minus our half of that, and half of that would just be 0.75. So in other words, we've actually got that the cylinder has a height of 0.75. And the cylinder would also then have a radius of 0.75 because it's sharing it. So it's got a radius and it's got a length of 0.75. So with all those dimensions, we're now ready to start doing some calculations. Okay, well, the first one we'll do is we'll work with a volume. And we said that the volume of the capsule was the volume of a sphere plus the volume of a cylinder, where the sphere has a radius. And remember that the volume of the sphere is 4/3 pi, and the radius was 0.75 cubed. And the volume of the cylinder was the area of the base multiplied by the height. So the base was pi, radius squared, multiplied by the height, which was 0.75. Okay, so the area of the base, it was a circular base with a radius of 0.75. Okay, but if we just go back, we said that the radius of the sphere was actually half of that, because that's the diameter. So let's just edit over here and just say that that's divided by 2, and that's also divided by 2. So the radius was half of that. Only the height was 0.75. So let's just, yeah. The radius was 0.75. Let's just clear that out there. And let's just edit that as 0.75 divided by 2, because it was from there to there, which is half of this distance over there. So it's really 0.5 divided by 2. Once we've got that all information, now we can just go onto the calculator and just put all that data in. If we move it across here, then we've got our 4/3, and some of you might be quicker at this than I am, so you've already got an answer, times pi times our 0.75 divided by 2, which we are cubing. Okay, and then we're going to add our pi that we're going to multiply by half that radius that we're squaring, multiplied by half the radius, 0.75 divided by 2, and we're squaring that, and we're then multiplying it by 0.75. And what do we get? Oh, it didn't like that. So let's just go back. It really didn't like that. So we've got our 4/3, which was our sphere, and then we added on our cylinder, which was our squared. Okay, and then we had to multiply by 0.75, and then just close brackets. Okay, there we go. So we've actually got 0.5, and that's in volume. So 0.55. So that's equal to 0.55, and we were working with centimeters, so it will be centimeters cubed. This value over here is centimeters cubed, and that one would be centimeters squared times centimeters, which would be centimeters cubed. So that is the volume of that capsule. Over to you, Looney.
Okay, cool. Guys, thank you so much for tuning in. I'd just like to send a quick shout out to @Sasanda Beatbox on Twitter, @TVG, @Bessie1, and @Matasiwo. Thank you so much for tweeting us, guys, and for keeping in touch with us. Remember, we are going to take a very short break, but don't go anywhere because Dina will be back straight after this. Welcome back, Mindsetters. If you've just joined us, we're with Looney and Dina. We're going over measurement for term 3, grade 11. So guys, remember, if you are stuck and you're not sure what's going on, and if Dina's going too fast, remember we do have the videos on YouTube. So all you need to do is go on to learnextra.co.za/live, click on today's date, and you'll see the notes are available and the videos will be available as well. So if you're a bit confused, you don't know what's going on, the video is there, so you can rewind it as much as you want. You can go through the notes at the same time, so you can go at your own pace. Dina's just on a roll here because she's excited about measurement and she's excited to be back for term 3. So I won't waste any more time. I'll take it straight back to her.
Thanks so much, Looney. Yes, it is. It's we've just been on holiday, so we're full of energy, full of beans, and we just want to get going. However, we have always prepared 3 sections for you, and in order to get through those sections, the speed is really the right speed. So if you are battling to keep up, then take Looney's advice and just go back and just go through it once again. Hearing it over and over again will certainly settle it for you. Okay, looking at the next question, I did look at the vitamin pill, the first question. Let's look at another object, and let's work with the surface area and volume of this object. The object that's given is as follows. It has a horizontal, or it's got a rectangular face with length 120, breadth 80, and then it's got a height into a prism of 20. So any of your cereal boxes, if you're having that for breakfast, they would be rectangular prisms. A loaf of bread would be a rectangular prism because it's got 2 squares or rectangles, and then all the other faces are perpendicular to that. And so that's exactly what's happening here, is that we've got 2 shapes. This shape over here which is a rectangular prism, and it is connected to this shape over here, which, okay, so I'm just going to draw in some lines. So this shape over there, okay, which is, if you look at it carefully, it's got a semicircle as its base, and then if it's got a semicircle on the other side as well, it would be a cylinder, but it's not a full cylinder. It's like a drum has been cut in half, so it's half a cylinder. Okay, can you all see that? Okay, so we've actually got these two shapes, and now we're going to treat them as individuals in order to work out its various volume. Now, volume is what I like the most because it's so much easier to calculate than the surface area. We don't have to look at all the faces in volume. So the volume of this one, I'm sure you'll all agree, would be the area of this space here, which would be a 20. Or 20 is the height, though. It would be 80. There it is there. So it would be 80 by 20. And then the height would be 120. So the area of the space multiplied would give me the volume of the pink prism. So the volume of the prism would be just the 80 times the 20 times the 120. The volume of half a cylinder, okay, because remember now we've got a semicircle as the base, so on the other side it's like taking any can or a drum and just slicing it longitudinally. We've got, it would be half of the area of the circle, so it would be half of pi, and the radius is 40, multiplied by the cylinder's height, which would be 120. Okay, so that would be the volume of the rectangular prism, and the yellow would be the volume of the cylinder. And we would just add them together, because those are not this solid here is not a standard shape. So we would separate it into its two constituent parts, work out its volume, and then work from there. Okay, what about the surface area? Okay, the surface area is always the area of all the faces that we see. So let's try and count them. We've got this face that we see at the top. Okay, remember, we're not breaking anything up. It's just the face that we see. So we see this face at the top, which is not the same as at the bottom. We see this face over here, which is being duplicated by that face over there. And we're seeing this face over here, which is the same as a face that's opposite that. So in other words, we've got two faces here, two faces there, and just one at the top. So that would be the surface area of the pink. The yellow would be the surface area of the semicircle, and then there's a semicircle that's opposite that. So those two semicircles would actually make a full circle. And then this portion here, remember the cylindrical portion of your cylinder, and the best way I can ask you to see this is just to take a toilet roll and go and cut it up. What is the area of that shape? It is a rectangle where its length is the perimeter of the circle, and its height, the height of the cylinder, is the breadth of that rectangle. So it would actually be this face that I see, there's another one that's opposite that, and then there's the cylindrical shape. So the surface area of the yellow would be the area of the circle, because I'm taking the semicircle times 2, plus the area of half the rectangle. Okay, so the area of the circle would be pi, radius is 40, plus the area of half the rectangle, which would be half multiplied by the height is 120, and the area of the base is a half of pi r squared, which is 40 squared. Okay, so we have, if we were to take a cylinder and we'd now cut it down the middle, this portion over here and the portion that's opposite it would make a full circle. So there's my area of the circle. And then I'm just taking this portion over here, which is half my cylinder, and that portion over there is the perimeter. So it would be half of the perimeter, which is 2 pi r. So there's an error over here. Let's just fix that. So let's just correct that. This rectangle that you open up to would have, that's the height of the cylinder, and this would be the circumference of the circle. But I'm taking half of that, so it's the circumference divided by 2. So it's not the, it's area of half the rectangle. So it's the height, which is 120, and the circumference is 2 pi r. So it's 2 pi times radius. Okay, half, it's because it's half the shape. And if you work all that out, okay, we would get okay, so we've got pi times 40 squared times our pi value, and then we're going to add it to 0.5 times 120 times 80 pi. And we're just going to close that. Times, my pi didn't pop up. There we go. And we can close that, and we get that value, which we can call it in terms of value. So it's 2106. So it's 20,106 watt. We were working in centimeters, so it's centimeters squared. So that would be the calculation of breaking it up into the faces that we see. But that's only the yellow portion. The pink portion, we said how many rectangles were there? There were 5, hey? So we had a rectangle. We had rectangular faces. And we had 5 of them. So let's go through them. If that is the height, and we had that as 20. So okay, so we had this as 120, we had this as 80, and we had this portion here as 20. And we saw the top face, but the bottom one is stuck to the cylinder, so we're only seeing one of these faces. So the rectangular faces would be 1 of 120 times 80 times 20, plus there are 2 of these, which is our 120 by 20. No, something's not right here. The top face is just 120 by 80. Okay. Let's go through that again. So we've got this face over here, and because it's a face, it's a 2D shape. So it's got 120 by 80 as the one. There are 2 faces of 120 by 20. And there are 2 of these faces that are opposite each other, and that would be our 80 by 20. And there are 2 faces of 80 by 20. Okay, if we go back, you'll see there's our face here. Okay, that's our top face, which is 120 by 80. and we don't see a second one of that because that one's glued to the cylinder. And then we see two of these, the 120 by 20, and we see two of those, the 80 by 20. There's one there and there's one here. So in fact, there are 5 of those pink faces, and that's what we've got here. The top one, and 2 of those, and 2 of those. And now we just add it all up. So we've got 120 times our 80 plus our 40 times 120 plus our 40 times 80. So we get 17,600. So we've got 17,600 squared centimeters. Okay, so surface area means working with each of the individual faces that you see until you've got all of them, and you keep going back to make sure that you haven't lost any along the way and that your measurements are still correct. It's tricky to do it on a board like this because we haven't got the shape and the calculations all next to each other, but it's important that you have that picture and that you actually take the picture and just work with parts of it so that you can see what's going on. The more pictures, the more calculations, the better you become at it. So I think we'll go for a quick break, and when we come back, we'll be talking about the volume and the surface area of a rondavel.
Okay, cool. Guys, we are going to take a very short break. I just like to read this Facebook post from Modise Flavor Mphahlele. He says, "Dope show today, Dina. I'm liking it. Season 2, Mindset, grade 11 maths with a smiley face." So dope, Dina, means that it's a nice show, it's cool, it's happening, and all of that. Thank you so much for your Facebook post, guys, and for your tweets. Remember, I did post the questions. Just a quick mention, guys. Remember that you must write down your formula. Especially grade 12s, grade 11s, and grade 10s. You guys must learn to write down your formula first when you are working out every question, because you'll find in exams that they actually give you marks for the formula. So always remember that one tip. We are going to take a very short break, so we'll see you straight after this. Welcome back, Mindsetters. I hope you guys are ready, your brains are fresh, you took some water, you had some juice, just to get you prepared for our last segment. Dina is with us and she'll be helping you with everything that you need to know about measurements. So Dina?
Thanks, Luni. And for those of you that don't know where the formulae is, there was a question about the formulae. It is on the notes. Just go back. I have put all the formulae up there, so you can just check. And if there's any formulae that you don't know, you can really Google it. It will really pop up if there's some foreign or strange formula that we haven't seen before. Okay. I said to you I would come back and look at the volume and surface area of a rondavel, and we're going to make some assumptions here. The question was given in the Clever, Keeping It Maths, the textbook from Macmillan. However, there are a couple of details that are missing, so we're going to fill in the gaps in order to be able to get to some kind of a nice answer. Okay. Right, so here's a model of a rondavel, and it says Benjamin has a model of a rondavel and wants to increase it by a scale factor of 3, so he wants to make it 3 times as bigger. And we need to calculate the surface area and the volume of the current model and also of the new model. And in terms of surface areas and volumes, your area will always be scaled up by a factor of a squared number, whatever your scale factor is. Because if you imagine that you're multiplying a measurement by another measurement, and measurements for area is always in squared units, then if they say that they want to make the values 3 times as big, your area is not going to increase by 3, it's not going to be tripled. Your area is going to increase by 3 by 3, which is going to increase by a factor of 9. And your volume is going to increase by a factor of k cubed, so it's going to increase by a factor of 3 by 3 by 3. So you triple the measurements. You would take, if this cone is 3 centimeters in height, then the new cone is going to have a height of 9. But the area will be multiplied by 9, and the volume will be multiplied by 27. So we will write up later on how surface area and volume work, but let's go back to the rondavel. Okay, so here's a rondavel, and it's got the following dimensions. It says that the model has got a height of 3 centimeters, that this is a cone, The roof is a cone, and it's made up of, with a radius of 5 centimeters. And then it's got a body, if I can call it that, and the height of that body is 6 centimeters. But the body shape is actually a cylinder. If you can imagine that rondavel's got that cylindrical shape. And the cylinder's radius is 4 centimeters. Okay? And we'd like to work with the area and the volume. Now, there's going to be some assumptions here. We're going to assume that the doors and the windows are closed, so that we're taking the solid as not having any gaps. For this particular calculation, we're going to make that assumption because we're not going to be using paint or anything. We're just working out the core surface area and that. And we're also going to assume that because the rondavel is on a patch of ground, well, in reality, it could be on a patch of ground, that we're not going to take, we're not going to lift it. We're going to assume that it is actually connected to the ground. So what we see is then the cylindrical portion, and we see this. And I'm making those assumptions. I'm saying that's part of how we're going to be calculating this. You could be calculating it in a different way, depending on the instruction. But in the absence of instructions, we're going to fill in those gaps. So we're going to say, let us work with these conditions. So we are setting some conditions at the outset. Okay, so I don't think it's difficult to see that we're working with this shape over here, which is our cone. And we're working with this shape over here, which is our cylinder. And we are making some conditions. We're saying that this rondavel is to the ground, so we only see the cylindrical portion, and we only see this cone. Okay. But can you see something else that we can also add to the surface area? And that is that there's this overhang. So there is this area underneath this cone that we would also have to work out. Okay, so I still maintain that the volume would be the easiest to calculate. So if we took the blue volume, which is the volume of the cylinder, let's just put it in there, volume of the cylinder, we're quite happy with that. We know that that is always the area of the base multiplied by the height. So it would be pi r squared multiplied by the height. And the volume of the cone, can you remember what that was? The volume is 4/3 pi r cubed. Okay, so can you see it's really, really easy. Our radius has been given to us as 4, so that's 4 squared. Our height has been given to us as 6, so it's just a simple substitution. And the radius of the cone is given to us as 5. So the volumes are really sorted out. We've got all the measurements we need, okay? So that would be assuming that the door and the windows were covered. Now, the surface is a little bit more trickier because it's not as straightforward since we've got this overhang and we need to work out the area of that overhang. How do you suggest that we do that? Okay. And also, if you remember, the area of this curved surface is, has got a formula of its own. If you remember, it's pi rs, where s is the slant height. And we're looking at this, and we don't have the slant height. We've got the perpendicular height is 3, the cone radius is 5. How do we work out the slant height? That's a good question, hey? So the slant height is calculated by taking the height, the perpendicular height of the cone, drawing in the radius, and the slant height of that cone, okay, will be the hypotenuse of a right-angled triangle. Pythagoras is always coming to our rescue. How's that? So we have 3, we've got a cone radius of 5, and so our hypotenuse would be equal to 25 plus 9 would be 34, so that would be the square root of 34. Okay, so we now have the slant height, so we can now work out this pink area. So we can work out the pink, we can work out the blue. How are we going to work out the leftovers of that overhang? Okay, let's try and draw some pictures and just see what's going on there. Okay, so let's assume that this is where, if we could see it, that circle, if you had to take that roof off, all you would see would be a circle. And that circle, in fact, it's not, this is an ellipse. Okay, I'm assuming that we see it as a circle. So it would be a circle of the cylindrical part. Then you put the cone on. The cone has got a bigger circle that it falls on. So this becomes the cone meeting the actual structure. So this portion becomes the overhang. This portion over here becomes that overhang. And so you've got a circle superimposed on another, where one is bigger than the other, creating the overhang, but the overhang's area is just that. It's almost like that donut shape. And the donut shape has got, because this is a hole, it would be working with the total area. So that would be the total radius, or the big radius. And we would take away this white area, and that would give us the area of that ring. Okay, so I've done a visual of, if you had to take the shapes apart, you would see the top of the building as a circle. You would place the cone on it so that the cone would cover that completely. But if you had to cut through, you would see that the cone superimposes that white piece. So the overhang, this left over here, is just the yellow area multiplied by the yellow area, take away the white area. And that would give us the area of the ring. So to go back, we would need the pink area, we would need the blue area, and then we'd need the area of the overhang. That would be our surface area. So let's try and put that together. So so we've got the surface area would be the surface, would be the cone, plus the cylinder, plus the overhang. Okay. Now, the cone's area would just be pi s. That is always its formula. The cylinder would be pi r squared times height. And then the overhang would be the pi, the big circle squared, minus the small circle squared. That would be the area of that ring that's left over. Okay, let's try and remember this. The radius of the cone was 5. The slant height we worked at as root 34. The radius of the cylinder was, can't remember that, was 4. And the height of the cylinder was 6. Then the big radius of the cone, what was the radius of the cone? It was 5. So that was 5 squared. And the little radius we've just worked out is 4 squared. Okay, so let's just click our precious calculator and let's put all this in. Let's see what happens. So we've got pi multiplied by 5 multiplied by root 34, and then we're adding pi, which we are multiplying by, that's 16 times 6. And then we're adding 25 pi. And we're also going to take away our 16 times pi. What does that give us? 421. So that would be our surface area. 421,5. So let's just 421,5. Remember that was a model, so it's centimeters squared. Okay, that was the little model that you were working with. Now we want to scale it up by a factor of 3. We can't just triple that, because what you're saying is you want to triple the radius and you want to triple S. So in the end, you're going to have multiplied it by 3 times 3. You're going to want to triple the radius, triple the height. You're going to triple the radius, triple that radius. So everything is being tripled. So in the end, okay, let's just extend that. The surface area enlarges by a factor of k squared. So if our scale factor was 3, then this surface area is going to enlarge by a factor of 3 squared, which is 9. So I've got to take our surface area of that and multiply it by 421,5 centimeters squared. Because we've got it on our calculator, we can just multiply it by 9, and we get 3793. 3793, and still centimeters squared. Okay, so any enlargement that you do on any of the linear measurements, with area they become squared, and with volume they become cube. So when we spoke about that the volume was just these two values, and if you had to calculate, if we were to enlarge the volume, okay, so let's fill that in. Okay, so volume of a solid enlarges by a scale factor of always a cubic factor, so k cubed. So in our question, our scale factor was 3, therefore the volume of the rondavel of the new model would be 27 times the volume of the original, because k cubed would be 3 cubed. So that's how the volume would change. Okay. Right, so that was the rondavel. I've got one last question, and that's just a very algebraic question. But it's something that, for those of you going into calculus and going into mechanics and going to all those nice subjects, it's good to know, is to compare if a cone and a sphere have the same volume and the same radius, calculate the height of the cone in terms of r, which is the radius. Okay. And really, this question is all about formulae. If you don't know your formula, you can't work with this. So you've got a cone whose volume you want, and you've got a sphere who's got the same volume. And they've also got the same radius. So there are some assumptions we can make here based on the given information. Same volume, same radius. So I'm going to call my cone, the volume of the cone, is always 4/3 pi r cubed. And the volume of the sphere is always I think it's the other way around. The other way around. This is a sphere. Okay, let's just do this. Let's go there. Volume of a sphere is 4/3 pi r cubed, and the volume of the cone is 1/3 of the area of the base multiplied by the height. Okay, so I just want to go and correct here, because we think, yeah, the volume of the cone here, that's not correct. We need to just correct this here. The volume of the cone is 1/3 of the area of the base multiplied by height. Okay, it's the sphere's volume, that's 4/3 pi r cubed. So if we go back to there we go, then we can say that 4/3 pi r cubed is equal to 1/3 of pi r squared. Remember, they've got the same that. So the 3's cancel, the r squared cancel, so pi's cancel, so we're left with a height is 4r. So if you're going to have a volume, if you're going to have a cone and sphere's volume is the same, then the height of the cone is going to be 4 times that of its radius. And on that note, I'll say cheerio. Over to Luni.
Okay, cool. Mindsetters, thank you so much for tuning in. Thank you to Macmillan for giving us a great show. We will see you same time, same place next week. So goodbye from us.
Previously, let's just extend the page there we go. So if we work with, let's do some coloring in, a right prism. Okay, the definition of a right prism is that it will have a characteristic face and all the other faces are perpendicular to that characteristic face. So for example, the very famous right prism that we know would be a cylinder. Because what you have is you have 2 faces that are circles, and then the other face, which is a rectangle, like a toilet roll. If you cut it up, you'll make a rectangle shape, and that face is perpendicular to the 2 circles. So in a right prism, the reason it's called right prism is because you have congruent faces facing each other. So another shape that you may have seen in the shops before is the Toblerone box. The Toblerone has 2 triangle faces, and then all the other faces are perpendicular to
Welcome, Mindsetters, grade 11s. It is your time, term 3. We're back, guys. I hope you guys are excited. I am Luni, and joining me in studio is Dina. Dina, how are you?
I'm very well. It's good to be here, and I'm excited for today's lesson.
Cool. So what are we doing on today's show?
Today's show, the first thing I want to say is to all the grade 11s I taught during the holidays. Hello, Tandeka, I know you're watching. And then I'll be doing some measurement that you've covered in grade 10, but I'll just be taking it a little bit step forward with a couple more of objects included into one unit.
Oh, okay, cool. So it's measurement, guys.
Yes.
So Dina, I'll send you to your board.
Thank you.
So Mindsetters, don't forget to join us and to watch and to just, focus and concentrate. Thank you so much to Macmillan for making the show possible. To keep in touch with us, guys, you can go onto facebook.com/learnextra. On Twitter, our handle is @learnextra to download the show notes, the videos, the schedules, to check out the...
So if you remember, from grade 10, we worked with the right prism, we worked with a cylinder, a right cylinder, we worked with a cone, and we worked with a sphere. And we've got formulae for the surface area, and we've got formulae for the volume, so it's dependent on what we're working with. And it's all about working with the faces. So let's go and have a look at some examples. We'll go through the theory first, just to make sure that you are with us. And then I'll work through a couple of examples which showcase possibly what you've done previously is worked with one shape. We're going to combine shapes to form other shapes into a unit, and we're going to work with the unit's volume or surface area. So I'm hoping that you're going to enjoy the lesson. So let's start with the revision. As I said, we're going to work through a few examples to calculate the volume and the surface area, as well as looking at some scale factors. We're not going to do a lot, but we'll touch a little bit on that. And here is the key concepts that you've learned.
Products that we have for revision and everything else wonderful, and learning more and learning extra and all of that. You can go on to learnextra.co.za/live. Remember, guys, I do post the notes on our Facebook page. So just remember to like our Facebook page. I'll post the notes and any other information that you will need for the whole show. So with all that said, and thanks to Macmillan, Dina, straight to you.
Right, everybody, thanks, Luni, and I'm really, really excited because measurement's one of those sections in maths that really makes sense. It's very practical, it's useful, and for those that are always asking, where will I use this? This is the right topic for you. You're going to be finding shapes whose areas you want, whose volumes you want to calculate. And so this is the mathematics for you, for those who are numerically minded as well and love to work with the numbers and number crunching. This is also the section for you. So let's get straight into it. What we're going to do is have a look at the formulae that we've used previously, either in grade 9 or grade 10, because we're really not adding anything new. The standard shapes have remained. We're not adding any new shapes, those two triangular faces. Hence, that is also a right prism. You could have a hexagonal base, and if opposite that hexagonal, you've got another hexagon that's exactly the same, so it's congruent to that, then if all the faces are at are perpendicular to those two, then we've got a right prism. So that is the features of a right prism. So a very popular one would be the cylinder. So let's just fill in here. We would have a cylinder as a very common right prism. The volume of that shape is then very easy to calculate, because if you've got two congruent faces, then if you imagine you had to shrink that and you had to build it up, then my volume is really made up of stacking those circles on top of each other until I have the full solid. So the formula for the right prism is always just the area of that, we call it characteristic base, because it's what defines the right prism.